Pittsburgh, Pennsylvania. My name's Steve Moss. I'll be your host today. Kind of our mission for today is to get people who are less familiar with CO2 to understand the new components required to use it as a refrigerant, as well as people that have a more advanced knowledge to maybe learn more about Danfoss products. Our agenda today. So we're going to start by going over the mobile training unit, how it's laid out, its design, and the various technologies used on the unit. Then we're going to talk about CO2. We'll break out everyone's favorite, the pH diagrams. We'll talk about our pack controller, 782B, that's controlling the components on this system. We'll briefly touch on our service tool software that we use to interact with that product. And then we're going to talk about parallel compression and high pressure ejectors, energy saving features on transcritical systems. And if time permits, we'll look at case controllers and our CC55 Connect mobile app for case controllers. So the unit itself, it's a medium temp CO2 transcritical system. We call it affectionately within Danfoss Big Red. If I can get a close up here, we're going to go over here. So as far as the construction of the unit, it's used all around the world. So we've got a buck and boost transformer that lets us use either 460 volt for the US and North America, and then we can switch it over to 400 volt for South America and the rest of the world that uses 380. If we move from there, inside our control panel here, we actually have 3 modes of operation. I want to make the point that all the components you see here aren't what's necessary for a small medium temp transcritical CO2 system. It's just this top row, and then we have it 3 times. So the top row operates just medium temp transcritical. We flip a selector switch. This will power down, and then the one below it powers up, and that's medium temp transcritical with parallel compression. Flip the switch again to application 3, and now we're medium temp transcritical with parallel compression, as well as multi-ejector high pressure ejectors. And then the balance of the components, again, to make the point that don't want anyone to have sticker shock that you need all of this because it's transcritical. For the system that we have, you'd have about 1/4 of what you see here in your control panel. So it'd be a much smaller control panel. And then before we move on, I just wanted to point out, if you have questions, if you can put them in the ask question box so that they're ready to go when we pause every 15 or 20 minutes for our questions. So our selector switch that I mentioned is here. I've got the unit currently set to parallel compression with multi-ejectors. Again, as I pointed out earlier, the selector switch will let this system manager 800A power up with the pack controller. If we select 2, this will power down, this will power up, and so on for application 3. So that's our power. If we come this way with the close-up, this unit is serving 2 medium temp evaporators in our walk-in box here. And there's a shelf in the walk-in box. If you look here, there's a shelf. We use that shelf for a couple of reasons. One, to access the gas cooler, which is beneath it, but we can also open that lid and create false load by discharging gas cooler heat into the walk-in box to keep the system running in cold ambience. Then our next close-up, if we go in front of the system here, just to kind of go over the system layout, these are our 2 medium temp compressors down here. Then we have 2 compressors on the left. Those are for parallel compression. One thing to note on transcritical systems, or really any CO2 system, you'll typically see a VFD on the lead compressor for each stage. So our medium temp inverter is here. Our parallel compression lead compressor inverter is here. If we come around to the left of the unit, we have our ejector block on this unit. So let's come around to the side. This is our multi-ejector block that we'll discuss later. Don't worry if you're not familiar with it at the moment. The vessel back here, it's kind of hard to see. This is our flash tank. It's really just a receiver, but in CO2, you'll learn why we call it a flash tank. To the right of it is our oil reservoir. To the right of the oil reservoir, kind of like a double-sized Pringles can, this is our oil separator that feeds our oil supply to the reservoir. Okay. And that's kind of an overview of the system at large. One last thing to note while we're talking about Big Red in particular, if we get a close-up here, we have 3 training stations that have all of the components we saw on the control panel earlier. we can get contractors or technicians familiar with our system manager, as well as the pack controller, the remote display for the pack controller, as well as case controllers. We have 3 stations like this on the unit. So having said that, I will bump through these slides that are going to kind of say the same thing. There's a picture of our 2 evaporators. This is the shelf that we were able to slide the lid to create the false load. And if you were to look inside of that, this is what you would see is the 2 fans on the gas cooler to discharge heat. One thing I didn't show in the close-up, but you probably saw in the photos earlier, was things that look like 2 large exhaust vents from, say, a dryer at a home. That's our discharge. So when our shelf is closed inside the walk-in, it discharges the heat from the unit. We talked about the 3 control modes. So we're going to start out with the refrigeration cycle. Talk about what is similar to an HFC and what is different from an HFC. And before we begin, I just want to point out, if you're familiar with HFC systems, you're 90% familiar with this system. You may not know it yet, but they're very similar. There's just a couple of new components that we need to discuss. So we'll start with everyone's favorite, which is our pH diagram. So if you're not familiar with this, to the left side of the diagram, you have lines of equal pressure. So towards the bottom of the chart is a lower pressure, and it increases as you go from bottom to top. Then we have lines of equal temperature. And if you'll notice, when we're within this dome, that stays constant. The reason for that is that's where we're changing state. So to the left of this dome, that's going to be liquid. To the right of it is going to be vapor. And in between, we're boiling liquid off to become a complete vapor, or we're condensing vapor down to a liquid. So outside the dome here, let me highlight the dome for you. Outside the dome, you have sensible heat that you can measure with a thermometer. Inside the dome, you have latent heat that doesn't change the actual temperature. It changes the state of the refrigerant. And inside the dome, by the way, is where we do 90% of our work. We do superheating and subcooling for other reasons, but the majority of heat transfer happens inside this dome. So we're going to start just by reviewing a basic 448A refrigeration cycle, just to kind of wet your whistle and get you in the early days when you first talked about pressures and temperatures around the system. If we follow our friend here, at point A, we're a low temp, low pressure, superheated vapor. So this is the suction inlet to the compressor at this point. We move across the compressor, and we add the heat of compression. We're now a high pressure, high temperature, superheated vapor. And we know we're superheated because we're to the right of the dome, which means we've boiled everything into a vapor. We've hit the saturation curve. Then we've added additional heat. So at point B, we're a superheated vapor. The first few passes through the condenser, we desuperheat. And then we hit the saturation curve. We continue through the condenser, where we condense back to a saturated liquid. And then by point E, we'll have subcooled a few degrees, and we'll be a high pressure, still high temperature, but subcooled liquid. And then we go across our expansion valve. That's the separation from the high side of the system to the low side is our expansion valve, much in the same way that the compressor separates it as well from suction to discharge. So we go across the expansion valve, we enter the evaporator, we flash off a little vapor here to cool down the remaining refrigerant. Then we go through the evaporator where we boil off the refrigerant until we're a saturated vapor. And then we superheat a little before we enter the compressor to make sure no liquid makes it back to the compressor. So we're going to take that same cycle and now look at it on a pH diagram to try and connect those dots. Same cycle. We're just showing it now so you can reference vapor and liquid and the dome liquid and vapor combination. So we went from the suction inlet of the compressor, across the compressor, absorbed the heat of compression. Now we're back up to the condenser as a high pressure, high temperature, superheated vapor. We desuperheat some, then we condense. We're boiling off as we come through the condenser. In the last couple of passes, we'll subcool a little. And then we go across the expansion valve. So we went from high pressure, 214, down to evaporator pressure at 44 pounds. And then we go back through the evaporator. We boil all the liquid into a vapor. And then we superheat slightly before we go back into the suction of the compressor. So that's our basic refrigeration cycle. And we want to remember liquid and vapor states. That's a really key ingredient to understanding CO₂, because with CO₂, we have a new thing. We have a critical point that we will operate above, which puts the refrigerant in a condition called supercritical fluid. The density of the refrigerant at that point is so dense that you can't really distinguish a vapor particle from a liquid particle. And basically you can't flash it off in an evaporator. So our system has to have something to bring us back into the dome, because that's where we get work accomplished. So I mentioned what's similar to HFC and what's different from HFC. The low temp portion of a CO₂ system, what they'll call a booster system, we don't have on our unit. Our unit is only medium temp for cost reasons and such. We didn't include low temp loads. But the low temp side of it is similar to HFC in that the high side happens all within the dome. So if you think of this and reference it to the HFC, you would see desuperheating, and then you're in a liquid state by the time you go back to the expansion valve, as well as on the high side of a medium temp transcritical system in a low ambient. It's still similar because we're below the critical point, and we are actually making liquid in the gas cooler, in the condenser. Where the difference comes in from HFC is when we're above the critical point of 87 degrees. Now the high side of our system is in the supercritical region. Excuse me. So now we're in the supercritical region. Excuse me, sorry about that. I choked myself. So a CO₂ system will, in a high ambient, we operate the high side in the supercritical fluid. Excuse me, in the supercritical fluid region. And then in the lower ambient, you'll see we're below that critical point. So the system transitions between these two, and most people will call it transcritical when you're in the supercritical region. And that transition from supercritical region here to subcritical region here is where that term transcritical comes from. But most people will refer to the system operating above the critical point of 87. They'll just call it's in transcritical mode. That's pretty commonly used across the industry. So I'm going to explain the new components needed to handle CO₂ in the way that it makes sense to me. I like to learn things until they seem simple, so I'm going to try and explain it to you simply. So we're going to take a 448 HFC system, compressor, condenser, receiver, and evaporator, and we're going to assume that we just evacuated that system and charged it with CO₂. We did nothing other than evacuate it, take the same system, and put 744 in it. So a couple of things changed because of the 744. The first thing would be that our evaporator pressure and our medium temp suction pressures are now at 400 pounds instead of 44 that they were with 448A, which is pretty high for suction, as well as on a 100-degree day, we're now 1,300 pounds at the condenser. So the first issue is going to be you burst all the piping because none of it's rated for 1,300 pounds. So that's a problem. And a couple of other things you'll notice is we have 900 pounds of pressure drop across the expansion valve. That won't work. I don't think selection softwares would even let you select that high. And then if you'll notice as well, we don't have liquid. Our liquid disappeared. And there's a reason for that. The reason our liquid went away is that at 100-degree ambient, remember, we're above the critical point. So when we get to this point, remember, we just charged a 448A system with 744. We didn't add components. We would basically get to here and nothing, we're above the dome. So it means we have no liquid. We're in the supercritical fluid region. Something has to get us from that point back down into the dome. And I'll give you a couple of moments to guess what that something might be. But if you complete the diagram there to get liquid back into the system, and think about what can we do to cause that to happen, think about the expansion valve. On the low side of the system or on a typical HFC system, we use an expansion valve to get us from the high side to the low side. No different with CO₂. On its high side, we're going to use an expansion valve. We call it the high pressure valve, but it's basically just a large expansion valve. So we call that valve high pressure. So the high pressure valve, the pressure drop across that valve is what takes us from the high pressure, 1,300 pounds, back down into the dome so that we can have liquid. Now we referenced a 100-degree ambient day. So in that condition, it takes 45% of the refrigerant to flash off, cool down the remaining refrigerant. And that's kind of an issue because it's a sealed system, and that gas coming back from the outlet of the high pressure valve, it has to go somewhere. Now, if we pushed it to the evaporator, if we sent that liquid to the expansion valve, we're only feeding the TXV half of the liquid refrigerant. And you could do that theoretically, but you'd need to double the size of your evaporator coils because you're giving it half the supply of liquid. That's not feasible. So we add a new component that we call the valve receiver or receiver valve. And its purpose is to take the flash gas from the top of the receiver and bring it over and return it to the medium temp suction line. And dealing with that flash gas coming across the high pressure valve, that's why the receiver is commonly called a flash tank. I've had people ask me in the past, where's the flash tank? They're thinking there's a second vessel. It's just what people call the receiver on a CO₂ system. It's still just the receiver. We're just dealing with flash gas at this point. So the receiver bypass valve, it serves two purposes. One, it just maintains a constant pressure in the receiver. Here we're showing a 520-pound set point. We want to keep that set point a fair amount above the evaporator pressure so we can still push liquid and help the system to circulate. But that also gives us a very stable pressure to feed the expansion valves. If you think about the receiver valve not being in place and the expansion valve at your cases seeing the changes at the high pressure valve, it would hunt continuously. It's a superheat controller. So having that variation all the time from the high pressure valve, you would have the EEVs chasing their superheat the entire time. So the receiver valve, it deals with the flash gas to keep it from going to the evaporator, but it also helps provide a steady pressure at the expansion valve. And I mentioned booster earlier. I just want to show this. It comes up in some later slides, and most people, when they hear they hear the term booster mentioned after it. So what booster means is that your low temp side of the system, the evaporators, as well as the compressor discharge, they go into the medium temp suction. So the medium temp suction boosts the low temp mass flow up to a higher pressure in the gas cooler so that you can still reject heat. That makes the low temp compressor also extremely efficient because of a low compression ratio. You've got a 2-to-1 compression ratio almost on the dot for your low temp compressor. So they're very efficient. You'll see small horsepower accomplishing a lot of work. And then the medium temp handles basically it has three connections, has medium temp evaporator return suction, discharge from the low temp, and then the flash gas bypass. And again, if you have questions along the way, please put them in the ask question box. We're going to pause in a few minutes and we can answer them and back up if we need to. So to kind of tie all of those together with kind of a diagram on the pH diagram without all the temperature and pressure lines to cause confusion, this on the left shows a basic system for transcritical booster. So we're going to start at 0.1 here, and we're going to fill this in on the right. So from 1 to 2 is going across the low temp compressors. So we moved up to 0.2. Then we're going to desuperheat a little when the discharge gas gets in that lower temperature header. Then we enter the medium temp suction. We go across the medium temp compressors. We're now up to gas cooler pressure. We're at the inlet of the gas cooler. And again, we're on the high side of our system, 100-degree ambient and supercritical mode. We go across the gas cooler, and all we're really doing on a 100-degree day is desuperheating. That's where the term gas cooler comes from. When you're above the critical point inside the gas cooler, you're not condensing. So the term condenser isn't really applicable. So since it's desuperheating, they call it a gas cooler. Just to note before we continue, if we were showing the 65-degree ambient, that gas cooler is certainly operating as a condenser, but it gets the nickname gas cooler and people just stick with it. So I mentioned earlier, we have an expansion where we flash gas off. That's our high pressure valve going from 0.5 to 0.6. So that brought us back into the dome. And you can see here that our percentages kind of line up. We're roughly 45% vapor here, about 55% liquid in the flash tank. So from the flash tank, we're going to exit the flash tank and enter the expansion valve for our medium temp evaporator. We then go into the expansion, we go through the expansion valve, we boil off, and then we return a suction gas superheated back into medium temp suction here. And that's 0.3 here on the left side. Then we're going to come back, send liquid as well down to the low temp evaporator. Again, go across the expansion valve, boil off through the evaporator, and we come back to 0.1, which is our low temp compressor suction inlet. The last piece of the puzzle here is 0.6 to 7 back into the medium temp suction header, and that's another expansion. If you'll recall, we had 520 pounds set point for the flash tank, 400 pounds for the medium temp evaporators. So that's our set point for medium temp suction. So that's an expansion. So we're coming from the flash tank over to the receiver valve and then back into the medium temp suction. And that kind of completes our cycle. There are typically questions around that. So hopefully we'll see some in a few minutes. And here we are for questions. Do we have any questions? So we have a question that's asking, do you need a parallel compressor for each compressor on the rack? The answer to that would be no. We have two here because it works out nice and tidy. We've got two evaporators, so we size a compressor for each evaporator, and then parallel compression. We were a little above what one compressor could handle, so we added a second one. But you're basically going to do a calculation by people smarter than myself, and they're going to determine the amount of flow that will be a gas or that'll flash off in high ambience, and you'll size the parallel compressors for that amount. So you're going to size them based on the system load. And to answer the question simply, there wouldn't necessarily be a relationship between number of compressors. Hope that answers your question. Next question is, will the recording of this session be available after the event? The answer is yes, it will be on YouTube. And then I'm also happy to forward the presentation to anyone that would like to look at it a little longer. I'm going probably a little fast because I'm nervous and I'm human, but I'll happily forward the presentation to anyone that wants it. Okay, so we have a question. Is the high pressure valve an end-of-life product now? If so, what will replace it? Just the receiver valve? Okay, so there has been some confusion around that. We had a controller called the 326A, and for a lot of years, it was the only controller on the market that would control a high pressure valve. It's made by Danfoss. That particular controller has reached its end of life and is no longer available. We have a replacement controller for that, which is our pack controller, the 572 model. It's not a drop-in replacement, but the kit that we sell comes with the transducers you'll need, the temperature sensors. But the valve itself, to answer your question, it's not going away. And on a transcritical system, it kind of can't go away because it's what gives us liquid to send to the evaporators. I hope that answers your question. And we have another question. In a booster system, if the medium temp compressor is shut down for any operational reason, let me get the rest of the question here. So the question was, if the medium temp compressor is shut down, do the low temp compressors also need to shut down? The answer to that is yes. Typically, it's tied into the software. Much in the way that when you start a system up, you charge the system, you get medium temp loads running first so that your compressors are running because they're kind of the condenser for your low temp compressors. But for that example, what would happen, let's assume on the left here, if we could switch to the unit view, let's assume that our parallel compressors here were low temp discharging into these two at medium temp. If the medium temp, for whatever reason, shuts down completely while low temp is running, our software shouldn't let it do that. But if it did, these would quickly trip on their high pressure switch. Because basically they would get a stop into the medium temp suction, quickly build pressure, and trip on the safety switches. So they would shut down on switches. Let's see, are the diagrams available to everybody? I'm not sure which diagrams we're referencing, but if they're contained in the slide, if they're contained in the presentation you're seeing, I'm going to send that out to anyone that's interested, so those will be included. If you're referring to the diagrams that are behind me or plastered around the wall of the unit, we can make those available to anyone interested. And then we have another question, what's the best way to charge a CO₂ system? So that's an excellent question. So charging the system, the first consideration is that CO₂ below roughly 60 pounds per square inch would be in a solid state. It forms dry ice. So if you pulled a vacuum on a system and you took a tank of liquid CO₂ and you just started dumping, you're going to form dry ice inside the system. So you have two tanks for CO2. You have a vapor tank, and then you have a liquid tank, and the liquid has a siphon tube down to the bottom of it. So you open your valves. We would open our high pressure valve. We'd open our receiver bypass valve, our expansion valves, and you want to charge the system with vapor up to roughly 100 pounds so that you get above the triple point and you don't make dry ice. Once you're above 100 pounds, you would then add liquid to the system, turn on one of your evaporators, and you get some load going, and you continue to add liquid as the store side of the system, the evaporators take it away. Keep charging with liquid, get your compressors running. Once you've got the entire system down to temp on all your low temp load, all your medium temp load, you continue charging the flash tank until you're above the bottom sight glass, and then the system is charged. So I hope that answers the question, but it's really important that you don't put liquid CO2 in a system that's below 100 pounds of pressure. So we have a question. Are you using the low temp evaporator as a low temp box, or is it used for refrigerant temperature control? But let me reread that. That didn't click. Are you using the low temp evaporator? Okay. So they're asking if you're using the low temp evaporator as a box, or is it used for refrigerant temperature control? So if the question is about the big red here, about our training unit, its walk-in box, this is actually medium temp. We didn't really have room in a 20-foot container to put either a low temp load or low temp compressors. But this is just a walk-in box. We've currently got it running at 35 degrees, pulled down to temp, so the system would run for today's training. Temperature control, I think I caused confusion earlier when I mentioned we have a shelf to put gas cooler discharge heat into the box. We do that so to get the system to run. If we want to keep compressors running during a presentation, we slide that open. So we kind of use this for load control. But CO2 in general, a transcritical system, think of your walk-ins and your cases as the same way you operate with HFC. You're just going to have an electronic expansion valve instead of a mechanical expansion valve and a case controller per case. Okay, so the red and green lights on the flash tank. I don't see the red and green lights on the flash tank. If we're talking about what I'm pointing to here, this is basically, it's tied to a switch. Can we get a close-up? That's actually, I've never been asked that. Great question. So here, with CO2, one of the safety considerations with the high pressure, you have pressure relief valves on your suction header, your liquid line, your discharge line. They all go to a common header via flexible hose, and then that is piped over and outside of the store. For us, it's just outside the unit in this stainless steel piping, and we have a digital contact here to let us know that that's been installed or not. If we don't have this installed, the unit won't run. So the red and green light you saw is turned on and off by this. When it's connected and safe, the light is green. If it's disconnected and unsafe, the light will be red and the system won't run. So it's kind of a dummy light to tell me, hey, dummy, you need to connect the relief valve piping. Thank you. I hope that answered your question. You're doing good. Oh, so I got a comment. I want to say thank you to whoever this is. I got a comment that says, you're doing great so far. Don't be nervous. I super appreciate it, but I'm still super nervous. Okay. So I'm going to move on to the next. Let's see. Actually, we got another great question. How do you avoid bursting the pipes? So with CO2, I got a question yesterday from the audience here at a training. They asked the question, can you keep your existing cases? Can you keep your existing field lines? And really the answer to that is no, because CO2 operates at much higher pressures. Your HFC piping is not going to be rated. Your low temp side of the system is going to have safeties on it at roughly 59 bar, some for 45 bar on low temp, but it's going to well exceed what you would have. So the shorter answer to your question is that CO2 requires thicker wall piping, more robust compressors. You avoid bursting piping because you have to replace it with piping suitable for the pressures that are experienced in situ. Okay, we've got a question that says, so typical system customers run receivers at minimal capacity, CO2 charges at 100%. So CO2 actually, it doesn't charge to 100%. We charge the liquid line out to the store, feeding all of our evaporators to 100%. But can I go a close-up real quick, Josh? So to answer that question, back to our receiver here, again, flash tank and receiver are called the same thing. So here, this only gets charged up until it's above this line. So when I charge this particular system, when I come meet it at various training sites, I literally do what I said earlier. I'll make sure it's above 100 pounds with vapor. Then I will connect to this port here and start charging with liquid. And then I just look in the sight glass here, if you can look in there, and you kind of see a little river. I don't charge it all the way up because I want it to have some turbulence where I can see that I'm at the very top of this line, which is how I simulate being above the bottom sight glass. So the balance of the flash tank from that point up will just be vapor, if that answers your question. So this one's probably charged to about 30% to get it above the bottom sight glass. I hope that answered your question. Can we have hot gas defrost option? Yeah, so the question is hot gas defrost available? It wasn't. These systems, by the way, we're training people. It comes across as it's new. They've been around a long time. There's over 40,000 of them in Europe, and they certainly have hot gas defrost. I think that's come up with it just in the last few years. I'll be honest, I haven't been on a site with a hot gas defrost system, so I'm not greatly familiar with it, but you can just kind of think of it, as think of it similar to like a heat reclaim valve feeding a hot gas line. You're going to go reverse piping through the evaporator around a check valve. It's very similar to the hot gas defrost you would see on an HFC, but again, at higher pressures. So you have to temper that pressure before you send it to the evaporator, because the high side of the system, from the discharge of the compressor all the way back around to the high pressure valve, that's rated at 159 bar. The evaporators on the other side of that, they're at 59 bar. So there are some components necessary between the discharge heat that's available and what you send to the evaporator. It's a little complex, but very doable. Parallel compression just there when you need more compressor to handle the load. Is there another reason? Great question. Question is parallel compression there for when you need more compressor load, or is there another reason? That's what we're going to jump into here in about 10 or 15 minutes. Short answer is it serves a different purpose. It's going to deal with the flash gas that builds up in the top of the flash tank. They're going to handle that load at a higher temperature so that we can have energy savings dealing with that refrigerant that's kind of already spent at that point. All right, so the ejector. So the questions on parallel compression and ejectors, I'm going to hold off on answering for the moment because we're going to cover that. I think the material is going to answer the questions. Let's see. So I do have a question about, can dry ice form during operation from inaccurate transducer readings? During operation, the answer would be no, because you're going to be about 200 pounds on your low temp side, not much below that. 200 pounds, I believe, is minus 22 or minus 20. And then you only go up from there. So flash tank is at 520, medium temp is at 400, and of course the discharge side, 800 to 1400. So you're never going to really see conditions of below the 70 pounds that would cause you to form dry ice. Yeah, we have another question about the oil system that I'll touch on in a little bit as well. And to answer the question, for the moment, it is different than what you see on an HFC rack. So I'm going to progress to the next part of the slide. Do want to mention we're capturing all of the questions, and I'll respond to all of them personally to make sure nothing gets left unanswered. So I'm going to move in just quickly. I'll go through this quickly because I don't know the audience, but I'm going to assume most of you are familiar with most of this. So our controller, our product line that we use for commercial refrigeration, this AK, it's on the front of every part number we have. It stands for Adapt Cool. That's the name of our product line. And then you have the hyphen, and then PC stands for pack controller. So some of our other products, the AKCM, that's a communication module. AKXM, that's an expansion module. So this kind of follows that. And we call this wonderful and amazing controller you can see on your screens now the PC782 pack controller. I want to just briefly touch on how we use that to control a transcritical system. So we're going to look at the sensor abbreviations that are confusing for some, and then we'll touch on the main control areas. So this is kind of a basic overview of our medium temp transcritical system. There are really four, I'm sorry, my apologies. Let's look at the sensor abbreviations. I get a few complaints about this, like they're confusing, but I think if you hear the logic, they make perfect sense. So first one we'll look at is the suction pressure. Most people are used to seeing that called SUCT-PSI. For us, the P represents a pressure transducer. The O represents outlet of the evaporator. So our line coming back from the cases, we want to know the pressure leaving the evaporator. So that's pressure outlet. Then we go up. S, the uppercase S means it's a temperature sensor, and it's on the suction line. Temperature sensor on the discharge line. Pressure transducer on the line to the condenser. S3C, I don't have a good answer for. It's an anomaly. S means temperature sensor. C, I'm guessing, means condenser. The 3 is a mystery to everyone. And we're not changing it. So there's that. Then we have a temperature sensor on the gas cooler outlet. A pressure transducer on the gas cooler outlet. Now we have a new one, the V for valve high pressure. A pressure for the receiver. And then the valve for the receiver. So the uppercase letter, and this is all through our software and various controllers. P represents a pressure transducer, then the descriptor. S represents a temperature sensor, then the descriptor, and then the same for the V for valve. Now that face that just went across is because I just discovered that PowerPoint has motion paths. I'm childish and I could not help myself. So in our mode 1, we're going to look at these. We're going to go through mode 1, which is just using the medium temp compressors. Then we'll talk about parallel compression. Then we'll talk about ejectors. So mode 1, we've got 4 basic control areas. We've got the suction groups we need to control. We need to control the fans on the gas cooler. Got to control the high pressure valve as well as the receiver valve. Those are our main components. Here's how we're dealing with return from the evaporators. Here's how we're dealing with the discharge heat of the compressors. Here's how we're getting liquid. And then the receiver valve is dealing with the gas in the flash tank by bringing it back to the medium temp. So we're just going to focus on the high side. So I've cut off any cases below or from cases. So again, these are controlled by our wonderful and amazing, powerful pack controller. So we're just going to take a caption of the 4 areas we identified. So coming into our medium temp suction, we've got return from the flash tank, where we're venting off the flash tank, as well as our suction line return from medium temp evaporators. The sensors that we need for that are going to be the evaporator outlet pressure. We've got a sensor on the suction line so we can monitor superheat, so we can do something if we realize we're getting liquid back. Then for alarming and compressor safety, we have a sensor on the discharge line as well as a pressure transducer on the line to the condenser. So those are all inputs. So we've used 4 inputs so far, all analog inputs. And then our devices are going to be our 2 compressors. So there's a couple of relay outputs that we're going to turn on and off. And then we'll have an analog output to send 0 to 10 volts to our inverter. So the set points for the suction group are going to be the TO set point. So that's our target temperature. It's something to note that this isn't the word to, like going to the store. This is actually an acronym like we saw on the sensor abbreviations. It's a new one. When you see the T, that means it's a pressure converted to a temperature. The reason that we do that is it's very common, maybe even on some of our legacy devices, that you put your set point in for your suction groups as a pressure. And so that causes you to need a PT chart everywhere you go, either in an app or in your pocket, to pull out and determine plus 20 means 44 pounds. 44 pounds is my set point. We simply do that lookup in the background for you. You just put in the temperature you want, and then we reference this transducer and convert that to a temperature. And then as far as staging compressors, we use what we call a neutral zone strategy. And basically the neutral zone are limits above and below the target set point to where before you bring stages on and off so that you don't chatter the compressors and short cycle the system. So our neutral zone diagram, the illustration kind of goes like this. We've got an example here. Set point is plus 20, so that's our reference. And then our neutral zone is set to 4 degrees. So again, the neutral zone is like a deadband. It straddles the set point. So, we've got our set point here, and then we're straddling it with the neutral zone. So if you reach half the neutral zone plus the set point, which we've done here at this point, we call that the plus zone. If you go to one of our controllers and you look at a detailed status and you see plus zone, it means we're more than half the neutral zone above our set point. And plus zone means we're going to turn on the next stage of capacity. The opposite side of that would be what we call the minus zone. So once we turn that compressor on, it's a little too much. We've ramped down the inverter. The pressure's still falling. We get to this point, we enter the minus zone, Now it's time to turn the stage off. And then it'll float back up. When you're not turning something on or off, that's when you're actually within the neutral zone, which means you're no more than 2 degrees higher or 2 degrees lower than the set point that you define. And when you're in the neutral zone, you use the VFD to maintain capacity. So you ramp that between 30 and 60 hertz to keep you at temperature. And then there's a little highlight to show that here we're just moving, no call for going up or staging down. So if you go to one of our controllers and you see plus zone or minus zone, that confuses some people, but plus means I've either just added or I'm about to add capacity, and it means I'm still above set point +2, or I'm still below set point -2 if you see minus zone, and that'll display until you get back up into the neutral zone, at which point it'll just say normal control. So that's our suction group control. The gas cooler fan control is actually really straightforward. So we've got our lines coming from our medium temp compressors, the discharge coming into the gas cooler, leaves the gas cooler and heads towards the flash tank, really heads towards the high pressure valve and into the flash tank. So the sensors involved are just two. We've got S3C, which again, for unknown reasons, is the ambient probes called S3C. And then we've got our gas cooler outlet temperature. The gas cooler outlet temperature, I just want to point out from having done a few startups and finding these largely not installed correctly, needs to be within 3 feet of the exit of the gas cooler. You've got high temperatures. The lines typically aren't insulated. And if you put it 6, 8, 10 feet away from the outlet, the temperature changes drastically. So it needs to be really close to the outlet so that it's getting the best picture of conditions leaving the gas cooler. And then devices, we simply have either an inverter or a 0 to 10 volt signal going to ECM fan motors. Something to note on that signal, typically for transcritical systems, people invert that and they actually control from 10 to 0, where 10 means fans off, 0 means full 100% capacity, so that if you were to lose that connection for any reason or upon controller failure, your gas cooler fans will go ramp to wide open. So those are our sensors and our device. The control strategy is pretty basic. We call it minimum TM, minimum temperature difference, but it's really just a delta between the ambient temp, which is the air coming into the gas cooler, and then the gas cooler exiting temp. We use a floating reference mode so that basically, as the ambient rises and falls, our 5 degrees difference just rises and falls with it. It's very similar to what's been done on the past with TD control. And then a couple of the key set points here. We have a gas cooler maximum reference, which means it won't let you float above a certain percent if it gets too high. And then what some people refer to as fast recovery. Our version of fast recovery is our absolute max. And basically, if you hit that temperature at the outlet of the gas cooler, it forces the fans to 100%. Another feature of the absolute max setting, it can shut down compressors if it needs to. It'll do what needs to be done to regain the high side of the system. So basically, the pack controller ramps the fans up and down to maintain a difference. One other quick note on the temperature sensors, these get reversed pretty often. And what that causes is the ambient would be here reading a higher temp than what it thinks is the outlet down here. So, it basically never turns the fans on. It thinks that it would make the gas cooler think that it's cooler than it actually is. So if you're struggling at a startup or in the field to get fans to turn on, decent chance that those two sensors got reversed. So the high pressure valve, this is one of the two new components that we need. If you'll remember, to get from the high side of the system in supercritical fluid region down into the dome where we have liquid and we can change state and do work, we needed the high pressure valve. The way this controls is kind of interesting. So the sensors, it makes reference to the ambient temp. The gas cooler outlet temp is extremely important to it. We've got a pressure on the gas cooler outlet. And then as far as devices, it's just the stepper valve itself. It's the high pressure valve. So what I said is kind of interesting is the set points. You just give it a minimum gas cooler pressure and you define a maximum. So think of that as like wintertime, low ambient. I don't want it to get below some certain amount. So let's say our flash tank, we set it at 520. We don't want the head pressure getting anywhere near that. So we'll set that at like 650, 700 pounds for our minimum. And then we set a maximum for a 110 degree day. We don't want it to get above 1,450 pounds before we relieve pressure to gain control of the gas cooler. But if you'll notice, we didn't tell it where it should be at. And some people call this the magic valve. That's why they call it that, because there's no defined set point, just a minimum and a maximum. And the reason for that is this COP line here. So there's a line on this chart here. What the valve actually cares about, this valve cares about where the gas cooler outlet temperature is in relation to this line here. What that line is actually, I think I've got it coming up on the next slide. My apologies. I got ahead of myself. So the valve is going to open and close to keep this sensor on this COP line here. So let's assume that my laser pen, let's assume that I were over here with the actual sensor reading. It was over here. The high pressure valve will lower the pressure to bring it back onto that line. And believe it or not, I could be over here and it will close a little to build pressure to bring it back up to that line. And the reason for that, so wherever it needs to be, whatever the pressure needs to change to get the gas cooler outlet temp back to the optimal COP line, that corresponding pressure is the setting. All that happens under the hood. It doesn't tell you anywhere what it's thinking. It's doing this hundreds of times per minute. So it is kind of magic. You just give a bottom range, top range. So I mentioned COP. You'll hear this thrown around a lot when people talk about CO₂. It stands for coefficient of performance. And we're going to spend the next hour going through this formula step by step until everyone is memorized. I'm kidding. The simple version of COP, it means work over energy input into the system. So for us, Q equals the amount of heat removed. Like we put energy into the system. The work we're accomplishing is we're taking heat out of our display case, rejecting it into the ambient air. And to do that, we have to put in a certain amount of wattage. So short definition of COP, heat removed divided by the power input into the system. So I mentioned earlier the optimal COP line. So at this point, I did an exercise several months ago. There's a formula about a mile long and take you all week to do it if you're a newbie to it like myself, that basically tells you for a given conditions, a given displacement of a compressor, how much energy does it take to compress that low temp, to compress the low temp suction gas, raise it up to gas cooler pressure at a given condition. So that calculation there, the pack controller is performing that calculation on an ongoing basis. So it knows the displacement of all the compressors. It knows how many compressors are active. It knows the ambient temperature. It knows the pressure leaving the gas cooler. And it works to keep the temperature exiting the gas cooler on this line because it knows as long as that is happening, that we're using just the amount of energy necessary to do this work. And that's all you want. There's really not a way to use less per se, but we want to use just the energy required. So the high pressure valve, while it does serve the purpose of giving us liquid and warm ambience, it really cares most about energy usage by your compressors and maintaining specific conditions in the gas cooler. And then on the control, the last one on the control, the fourth area that we highlighted is the receiver bypass valve. And it's very simple. It's looking at the pressure in the top of the receiver, and then it's using the receiver valve to open and close. So basically, as the pressure rises in the flash tank or the receiver, this valve opens to relieve some of it. As the pressure drops, it closes off to back some of the pressure up to raise it back up. Having said that, the key set points, you tell it what set point you want. We use 560 or 520 for our example, and then you give it a minimum and a maximum. One difference between the receiver valve and the high pressure valve is the high pressure valve will never be fully closed or fully open. If you fully closed it, you're going to pretty quickly, that's a dead stop. You're going to pretty quickly trip the high side of the system on high pressure. If you fully open it, you're going to trip your low temp compressors because at that point they would be the condenser because you're just sending all the flow, especially on a hot day. This valve, however, will close completely if it needs to build pressure in the flash tank, and it will open to 100% if it needs to relieve pressure from the flash tank. So it references the receiver pressure transducer and just does its thing. Troubleshooting wise, these are the two new parts of the system, the high pressure valve, the receiver bypass valve. And typically they're not the issue. Most people would think they are because they're not familiar with them. That must be the problem. But the high pressure valve, if it's a warm ambient and you're towards an open position, it's working. If it's a cold ambient, it's towards a closed position, it's working. The receiver valve here, if it's maintaining flash tank pressure plus or minus 5 to 10 pounds, it's doing what it's supposed to. So just a quick recap on the control, and we'll take some questions. Suction group, we're using neutral zone plus and minus control to control the compressors. We're ramping gas cooler fans to maintain a delta between these two sensors. High pressure valve references ambient and a lot of other things, but it's basically trying to keep the gas cooler outlet temperature on the optimal COP line, again, which is coefficient of performance. Higher the COP, the more efficient the compressor. And then the receiver valve open and closes to maintain receiver pressure. So I think our next item is questions. Any thoughts of safety for the service techs? You have more components and very high pressure. So there are some safety considerations. The first one that I saw, well, I'll say first that I haven't personally experienced. I've been to dozens of the sites running these. I've never experienced a pressure event other than sometimes you hear a relief valve chatter. You have a service valve that wasn't open, something like that, but that doesn't actually get on the service techs. That discharges into the relief header, which will be piped to outside the store. I have been on sites where had a vibrating compressor that cracked a discharge line. So you see kind of a little bit of a fog in the area. But safety wise, the only thing I've really seen that was dangerous was I saw a technician looking for a leak with his hand. And I personally feel like that's dangerous because if you're on the discharge side of the system, that could be 1,400 pounds, and even a little pinhole, it's going to be a lot stronger than your skin. So I would highly recommend not looking for leaks with your hand on a CO2 system. Worst case, if you want to use that method, get a piece of cardboard and use that because you don't mind if it gets cut. Past that, I haven't seen any safety concerns as far as things rupturing and getting on technicians. Okay, so I've got a question to go over the oil management solenoid. That is coming up after ejectors. I've got slides for that. So the symptoms of, okay, a question is, what are the symptoms of low refrigerant level and how is refrigerant level monitored? That's a great question. So you actually, most of the manufacturers will put both a high level switch and a low level switch because both conditions are bad. If you hit the high level switch, you got too much liquid in the system. You may have some variance in the system based on having reclaimed devices like that. The low level switch is important because if you're not sending liquid to the evaporators, you're not removing heat. The symptom would be is you're struggling with cases making temperature. You don't have enough liquid in the system. You can't pull everything down. So you would see temperatures rising. You should have gotten an alarm for that, by the way, based off the low level switch. And if you'll remember from earlier, we just charged the flash tank to above the bottom sight glass. And that puts you maybe 10 or 15% up the flash tank away from the low level switch. But yeah, if you went completely dry, you're just going to stop cooling and have high temperature alarms. So I have a question. If the system is completely empty, how do you get it above 100 pounds? And this would be in reference to, say, system charging or service work where you had to pull a vacuum on the system. So CO2 comes in two cylinders. You can get a vapor tank, which has no liquid in it, and then you can get a liquid cylinder that's stacked with liquid, and the takeoff is a siphon tube that goes to the bottom of the tank. If you had a system below 100 pounds, you would use a vapor tank to charge it above that. And again, you'd want to make sure valves are open throughout the entire system. Everything you evacuated needs to be accessible all the way back to the charging port, and you would use a vapor tank to get it above 100 pounds and then resume charging with liquid. So a question on how do I request a copy of the presentation? You're giving the, thank you so much. So we're going to share the presentation with all attendees. I'll share that with you, and I very much appreciate your kind words. Okay, so we have a question on can you use Modbus on the VLT drive instead of analog signal? I believe the answer to that is yes. We typically use 0 to 10 volt kind of as our default. We don't want to lock people into Modbus like you have to use our product. We want you to, and our products are wonderful and amazing. They bring me happiness. But should you choose to use our competitor, we'd like to make that easy for you. We typically default to a voltage signal. Why is stepper valve required before the flash tank? So the valve before the flash tank, we call that the high pressure valve. It's basically, if you look at the refrigeration cycle on a pH diagram, when you're above 87 degrees, you're in what's called a supercritical fluid region. That can't change state anymore. You can't boil it or condense it to do work with it in latent heat. So we go across that high pressure valve. It's really like an expansion valve to reduce us down to flash tank pressure, which during that process, flash off some gas while cooling down the remaining refrigerant to have a supply of liquid in the flash tank. So we have a question: is the pressure relief valve stopped from opening if the controller can't get control of the high side of the system? What stops it from opening if the sensors are swapped? So the answer to that question is really no. So the good thing about there's a good and a bad side to a pressure relief valve. The good thing is it doesn't care about the controller. It's a mechanical device, and if it exceeds the pressure it's rated for, it's venting your refrigerant. So that's kind of a bad thing because we don't have control of it, but it's good because it doesn't rely on anyone's controller. It's going to protect the system. You want it to do that because you don't want to rupture piping. You don't want to hope it didn't hurt other components. A good side of it, though, is that most of them burp. They don't just open and discharge all of your charge. They blow off just enough to where the pressure on the incoming side of the pressure relief is below its set point. So you'll hear a chatter. It almost sounds like a child's little rattler machine gun toy. You'll hear a chatter like that. That means the relief valve is burping. And even if you have to add charge later on a hot day during a startup because you had those sensors swapped, you won't lose the entire charge. You'll just burp charge until you find the problem, and then you would recharge to get it back up to above your bottom side glass. Can the fans and high pressure valve fight each other? So that's a great question, and the answer is actually no. If you'll remember back, let me see if I can bring this up. My apologies. I'm going to jump slides, so the presentation, if it's on your screen, is going to look awkward for a moment. So if we go back to our fans. Okay, condenser fan control. All we're doing on condenser fan control is we're controlling between, give me one moment to jump back in gear here. So the question was, can the high pressure valve and the condenser fans fight each other? All right, PowerPoint is smarter than me for the moment. So if you'll remember, what we're doing is TD control between the ambient sensor and the gas cooler outlet sensor. So the actual fan speed control, it doesn't talk to the high pressure valve, doesn't care about it. Its only purpose in life is that whatever this ambient temperature is, I want to make my outlet temperature no more than 5 degrees above ambient. And it does that at all times. On the high pressure valve side of that, if we can see if I can back up here. On the high pressure valve, if we look back at how it controls, it doesn't really care about the delta between these two. See, one moment. My apologies for the awkwardness on your screens. So if we look back at the high pressure valve, remember the gas cooler fans, all they care about is the difference between these two. And then the high pressure valve, all it's really trying to do is make this temperature land on our maximum COP line that we saw earlier. So they are connected in the sense that what the fans are doing has an impact on the outlet temp from the gas cooler, but they don't necessarily fight each other. The high pressure valve would react as this moves to try and bring it back to that line. So there's never a chatter, which I think might have been the intent of the question. Hope that answers the question. So what leak detector do you recommend for leak checking CO2? So we actually have close-up, Josh. So we'll get a close-up here. There's a handsome gentleman behind the camera for the close-up you guys aren't seeing. I want to thank him for his help. So this is our DGS gas sensor. It's basically our CO2 sensor. Typically, you're going to have one mounted low on any refrigeration system. So as a Danfoss employee, I would recommend this gas sensor. If you're looking for leak detection that's permanent, if you're looking for a wand leak detector that you walk around and sniff the system with, I'll be honest, I'm not familiar with the different categories. The only times I've done that, I borrow it from the contractor. So my recommendation is borrow it from your friend. So we have a question that says, do you always want the gas cooler operating in the transcritical zone? So the answer to that is really no. It operating in the transcritical zone is based on ambient temperature. So if you picture inside the gas cooler, I've thrown out the number of 87 degrees several times because that's the actual critical point, but that's not really ambient. 82 degrees ambient would be your critical point if you're going to have the outlet of the gas cooler be 5 degrees higher. So at 82 degrees, you're really 87 inside the gas cooler. If the ambient gets below that, then you're going to be below the critical point and operating in subcritical. So it transitions between the two throughout the year, even on a summer day when you're 96 degrees at lunchtime, you're 72 degrees at night, you were transcritical at lunchtime and you're subcritical that night. So we have a question that says, are sites using CO₂, keeping additional refrigerant on site, the availability? Yes, they are. So it's asking about quantities. One thing I'll note on that I wasn't aware of till recently is the cylinder providers, Air Gas and such, they do charge a storage fee for you having their cylinder over long periods of time. So, especially people that are new with CO₂, it's new, it's different, it must be spooky. They'll get an additional charge to keep on site, like in perpetuity. But there is a cost to that. I don't know the dollar amount per cylinder. I think I heard the number of $30 or $40. But if you times that times 15 cylinders times 3 systems times 12 months, not financially viable to keep them around long term like that. And then is 744 considered refrigerant grade CO₂? So 744 is actually the identifier for the refrigerant itself. So carbon dioxide, its identifier is R744. I'm glad someone asked this because there are different grades. I believe the minimum grade that you would use, and this is based on compressor manufacturers, valve manufacturers across the board, is what they call Coleman grade. So you want to have a minimum of Coleman grade quality in the CO₂, and it's the percentage. They'll refine it and extract it. You might get lesser percentages for something like cleaning vegetables in an industrial application. But for refrigeration systems, you don't want to have any non-condensables. You're going to want Coleman grade or better. We're good? Okay, so we'll continue on. I need to back out to move forward in the presentation. So again, my apologies for that. I know it's painful to look at. So we're going to now look at parallel compression. So parallel compression is something, it kind of causes confusion. If you just walk up to a system utilizing parallel compression, it just looks like you've got more medium temp compressors. So what it does, if you'll notice here, we've got 2 compressors that are piped in parallel with the medium temp. In parallel, meaning that the line coming from the flash tank vent line comes this way, and then we go one path to the parallel compression suction, the other path through our receiver valve to the medium temp compressor suction. And then they both discharge up to the gas cooler. So in essence, piping wise, they're piped in parallel. They're compressors. So somebody chose the wonderful name parallel compression. What its purpose is we want to deal with flash gas coming off the receiver in a more efficient way. So on a 60-degree day, we're at 750 pounds. And if you'll notice here, I think we have the percentages. There's only 17% of the refrigerant that had to flash off to get it from down to our flash tank pressure. So at 17% flash gas, we're just going to send that straight into the medium temp suction line. Even though we've got 17% of the refrigerant in the flash tank that doesn't go to the cases and do work, CO₂ is a much better refrigerant. You're still more efficient than HFC to handle that 17% right into the medium temp. And also, it's not enough flash gas to keep one of the parallel compressors actually running. It would chatter and bang on and off, even with a VFD limiting the frequency to 30 hertz. So in cold ambient, you bought your parallel compressors for nothing because they're not used. However, you still have 100% of your load going to the medium temp, nothing going to parallel. However, in a warm ambient, they are brilliant. So in a warm ambient, we've got 43% of our overall mass flow turning into flash gas that we can't use that we can't use out at our cases to evaporate, absorb latent heat, and do work for us. That means 43% would be sent to the medium temp. That's bad because there's a better way. You purchased 2 compressors, pipe them in parallel. So we're going to close that receiver valve and force that load to now go up to your parallel compressors. So now instead of going to your medium temp suction, you'll see that path winds up at the parallel compressor suction inlet. So at that point, we had 57% of our mass flow is liquid. That went out and served our cases. That still needs to return to the medium temp suction. However, 43% of our overall mass flow was able to go to our parallel compressors. The way we get it to do that, there's a set point in our pack controller. The pack controller is wonderful, by the way. You tell it that at a certain percentage of opening for the receiver valve, close and activate parallel compressors. So let's say that was 30%. When we do that on that 100-degree day, we're now servicing that flash gas at roughly 30% better efficiency than we would have on the medium temp. So when this was first introduced, this was back when there was a misconception when transcritical first came around, maybe 10 years back, that you can't use it in warm climates. It will work in just about any climate. It just becomes inefficient because of the amount of flash gas you have to deal with. So the first step for addressing that was adiabatic condensers. And that's basically, if you're not familiar, it's a condenser coil. It's typically a V coil, and it's vertical, and they'll put a pad that they run water across to basically cool the air that the condenser sees, and it kind of lowers your condensing pressure. And that would let you push a transcritical system further south in warmer ambience and still run efficiently. To get even further south, they came up with parallel compression. It was a really smart idea. And it literally lets you save about 30%, depending on the difference between the parallel compressor set point and your medium temp suction set point. And just food for thought, the set point for the parallel compressors will be flash tank pressure. We typically will float that up. When we close the receiver valve, we'll float the flash tank pressure up about 4 degrees to maximize that savings. So that's what parallel compression does. And on this system, on this unit, it's these two here. When we're operating in parallel compression, we're diverting part of our load over to those compressors. So I'm gonna hit questions before we look at ejectors. So the question is, how is excessive venting managed during extended power outages? So there's a couple of options there. Well, really, there's one option. You either have a generator that will keep the system running. Some customers will put a small condensing unit in a heat exchanger, so literally just to pull heat. So if you think of we're venting through the receiver valve, they can put a heat exchanger between the flash tank and that receiver valve, and they can take any heat buildup and run it off of a small condensing unit in a heat exchanger to manage that. That still requires that you have some type of auxiliary power. And then the other thing is that it just vents the charge. I can't stress enough that the vent valve doesn't just pop open and vent the entire charge. It pops open until the pressure on the downside, until system pressure gets below its rating, and it reseals. So it kind of burps. It makes a chattering noise, but it's going to just burp slowly over time. My guess would be that you'll lose charge during the day, and then like this system, it's fully charged. We closed it up overnight, 70 degrees. It didn't vent anything. You're not going to lose your charge all at once, which I think is kind of a common misconception because the valves kind of burp. I don't want to say an actual time because I don't want to be held to it later. The question is, if the relief valve burps, should it be replaced? That would really be an OEM manufacturer's recommendation. My personal thought, I've seen them burp hundreds of times. I've never seen one replace it because it burped. But again, that's my own opinion and not the opinion of Danfoss Incorporated. All right. We have a question on flash tank and other devices on the rack. I believe there is a red and green light. One or the other means feeding. 4 pulse means feed, or am I wrong? To properly answer that, I'd have to know if you're talking about on a control board. I get the feeling that it may be thinking of where it wires into the control board. There's status LEDs, stepper module. And there's actually, I don't know them off the top of my head, but you do have a different blinking sequence and number of lights that tell you if the valve's opening or closing. You're also able to, with our service tool software, you can manually override the valve to certain percentages. That's part of the startup procedure, is to stroke the valve, put some pressure, watch it relieve when you think it should be open, and vice versa. But I think there's no indicator lights on the valves on the unit themselves, but I think on the stepper boards, you can see what they're doing that way. But you also can see what they're doing through the pack controller or through the system manager as well. Okay, next question is, will low temp compressors always have a lower percent liquid going to the medium? Let's see, going to the set. Medium temp has the valve to flash off. Okay, so that's a good question. So the question was, is the medium temp going to get more liquid or is the low temp going to always get more liquid because the medium temp has to deal with flash valve? So as far as the liquid feed going to the cases and the actual expansion valves, that's coming off the bottom. That's coming off of our flash tank, where our liquid's above the bottom sight glass. So we've got a solid liquid feed going to the store for both medium temp and low temp. The flash gas is on the top of the valve, and we take that vent off the top, and that's what gets diverted to the medium temp suction. So the medium temp suction is taking that around the evaporators. It's all done here at the system. The evaporators will all get 100% liquid, both medium and low temp. So we have a question about today's slides. We are going to send the slides to anyone that's interested in having them. We will send that out. I believe we're going to put this on a YouTube channel, but I'll make sure and get with our wonderful marketing team here. We will send the presentation to anyone who wants it. And let's see. So we have a question. Does the controller exercise the parallel compressors when they are unused for long periods of time? I believe the answer to that is no. There's logic. There's some built-in open logic within the pack controller that you could do that. There's a way to make it do it, but I don't think by default people just generally, I don't think by default they're exercised. So we have a question. Have you seen any issue with the compressors vibrating so strongly at a certain hertz on the VFD? Yes, I have. So the question is, have we seen vibration issues at random hertz from the VFD? And the answer is yes. I mentioned earlier having seen one with the discharge line broken. The solution to that, other than it not being properly supported on the system, they also wound up skipping like 41 to 44 hertz or something. That's where the vibration was occurring. And in the VFDs, you're able to program in steps to skip. So you can program it in to where it'll skip certain hertz that are causing vibration. But yes, that does still happen on CO₂. I think that's with any inverter and compressor scenario. Every now and then you get that magic setup that causes some issues, and you use hertz step skips to address it. Okay, so we'll move. We're going to now look at ejectors. So people have heard the term multi-ejector. Didn't make sense when I first heard it. I was kind of reflating it to liquid injection into a scroll compressor, things like that. It's very, very different animal. So the ejector, if I can get a close-up, that lets me aggravate Josh for a close-up. So the ejector block looks like this. We had one on the other end of we showed it on the other end of the system earlier. This first piece, this is going to be our screen. It's removable, serviceable filter screen, and all of the flow coming from the gas cooler will travel through this screen. And then here we have various ejector blocks, is why it's called the multi-block. That ejector inside it looks something like this, where this is your gas cooler flow. This is medium temp suction return inlet, and this is the exit to the flash tank. So that device we see on the slide, thank you, Josh. So what we see on the slide here is an ejector port. And I mentioned earlier that I like to study things until they click in my mind simply. So I'm actually going to equate this to something I think most of you will be familiar with. So entering the actual ejector itself, the device we just looked at, we've got the mass flow from the gas cooler. We've got the medium temp from the suction cases coming in the little, looks like a revolver barrel portion. And then those mix together and they exit and return to the gas tank or to the flash tank. So for me, this kind of reminds me of a wand for a pressure washer. Pressure washer wand does the exact same thing using a Venturi effect, which is kind of what we're creating here. So if we travel through this, the ejector again, we go from the gas cooler inlet. So that's our high pressure water going into the wand of the pressure washer. So we're to that point on the pressure washer wand. Then we bring in the medium temp suction from the cases, which we haven't explained yet, but we're going to. Just trust me for the moment. This is the suction return from medium temp comes in here and joins the gas cooler mass flow, which is not unlike the soap solution from the tube that drops out of your pressure washer wand. And then the two mix together through the mixing chamber here and then exit through the diffuser. Very similar to our pressure washer wand. They mix together here and then exit as a soap and water mixture. So our soap and water mixture for the pressure washer example is our gas cooler and medium temp return gas mixture. One thing to note is that similar to parallel compression, you're only going to get this effect when you're in high ambient conditions. So having said that, think of the ejector working when you've pulled the wand with the trigger on the pressure washer wand. We only get that Venturi effect when we've pulled the trigger. So that Venturi effect goes something like this. The ejector block we looked at earlier, we've got our high pressure inlet. On this example, we've got 3 off and 3 on. So we come through the ones that are open. We travel to here. At this point where they mix, we're restricting the flow. And by doing that, we create a low pressure area, and that creates our Venturi effect, like the pressure washer does, drawing the soap solution up and mixing it with the high pressure water. So when we create that low pressure, we actually create a lower pressure than our medium temp suction at 400 pounds. And that's going to cause our medium temp return gas, which we've now piped back towards the ejector block, to draw into this. They call it lift. It's going to cause a lift to bring that. It's going to come into the ejector. It goes up here and mixes with the gas cooler. Then it goes through the mixing chamber and exits and all leaves together and goes back to the flash tank / receiver. So we come to the top. This is coming from the gas cooler. We come here. We restrict the flow. We bottleneck it. That causes a low pressure situation with a Venturi effect that draws in our medium temp return gas. Then they mix together and they exit and they go together down into the flash tank. So the benefit of that looks kind of complex. You wonder, well, what's the benefit? So we talked about parallel compression and what that does. So these will always be used, just food for thought. The ejector block is always used in conjunction with parallel compression. You can have parallel compression without the ejectors, but not ejectors without parallel compressors. So again, much like the parallel compression option, you paid for all of this. It's a 60-degree day. It's not really going to do anything for you. We only got 17% flash gas at 60 degrees, and we already know that's not enough to run the parallel compressors, and we're okay running it on the medium temp because of the efficiency we get from CO₂ as a refrigerant. So on that 60-degree day, you're going to get 100% of your load still going all to just the medium temp compressors, not using the parallel compression at all. One thing to note, we're showing the high pressure valve and the ejector block. Most people are doing that because they have the high pressure valve as backup. But you don't have to have the high pressure valve. But if you want to purchase it every time, we're okay with that too, obviously. So here we'll notice nothing went to parallel compressors. And the reason is we haven't pulled the wand, the trigger on the pressure washer wand. Back to that example, there's not enough pressure drop across the ejector block. And there's not enough mass flow because it's a cooler ambient. We're not running everything. We can't create the Venturi effect. And this is a new line here. This is our suction accumulator. We piped from here over to the inlet of the ejector block. Now let's look at this with a warm ambient. So now we're at 100 degrees. We're back to our 43% flash gas in the top of the tank and 57% liquid going out to serve the store. So we've already determined that sending that 43% to the plus 18 is a bad idea. We're going to move that up. And again, that flow is going to make its way over to our parallel compressors. However, since it's 100 degrees, we're using full operation of the ejector block. I spoke too soon. We're going to look at the 57% liquid right quick to help explain the ejector. So of that 57% liquid going to the evaporators, the low temp makes up about 35% of that. The medium temp is going to make up about 22% of that. So at this point, the refrigerant coming from the medium temp evaporators has a decision to make. Do I go to the plus 18 at 400 pounds, or would I go somewhere else? If we've pulled the trigger on the wand, meaning we've got high pressure drop across the ejector and we've got high mass flow, we're going to create a condition that makes that 22% go to the left on our diagram, and it's going to slowly weave its way back over to our parallel compressors. And the magic of the ejector block is this. At this point, we're now running 65% of our overall system mass flow on a plus 36 compressor. And that includes serving the plus 20 medium temp evaporators. And that only leaves 35% coming to our low temp, or to our medium temp, because all it's doing now is servicing the low temp load and compressors. So at that point, with the ejector block working on a 1 day in parallel compression, 65% of your overall mass flow is being handled at almost 30% better efficiency than it would be without the parallel compressors and the ejecting block. So here, if you'll remember, we got 43% efficiency before without being able to pull the 22% over. So with no ejector block, 43% efficiency, add the ejector block, you're getting 65% back up to that higher efficiency. And that's really the purpose of ejectors. This unit in particular, this big red training unit has ran, I believe it was in Jordan, at like 125 degree ambient. So the myth that transcritical CO₂ and warm weather can't be friends, that's not been the case for many years. We're still trying to dispel it, but part of the effort here today is to explain this technology to try to get people to quit thinking of CO₂ can't be in warm weather. And I'll now take any questions that might have come in. So where is the ejector in the system located? So I'm going to bug Josh again for a close-up. So the ejector block on our system, it's over on the left side of the unit. This system was likely retrofitted with it, and that was the best place for it. But this is our ejector block here, and it is between the gas cooler and the entry into the flash tank. And then in parallel with this is our high pressure valve up here. We come around the front here. This is our high pressure valve. One thing I'll note, I mentioned earlier that you don't have to have both of them. There is some benefit to having both. In a low ambient condition on an ejector block, they're not equal stages through the different nozzles and ejectors, but you're only going to get maybe a combination of 15, 16 steps from the ejector block. Here you got 2,500 steps on the high pressure valve. So for low ambient, it does kind of make sense to have the high resolution of the stepper valve. And then when you get above a certain ambient, move over to try and get your Venturi effect, pull the trigger on the pressure washer wand, pull that load up to your parallel compression temperatures. I hope that answers the question. What determines when parallel compression is turned on and off? So what happens with the parallel compression? We've got I think we're okay without a close-up, but we've got a valve here, which is our receiver valve. We tell it in the software, if you look for the settings for parallel compression, there's not really an area. It's in the receiver valve settings. And you basically tell it, start the IT compressors. We call these IT for intermediate temp. There's low temp, medium temp, and then intermediate temp, which sounds better than high temp, I guess is why they chose intermediate. But you set in the software, I want at 40% receiver valve opening position, I want to turn on parallel compression. The way you turn on parallel compression is simply closing the receiver valve, which forces the load to go that way. So if you think about the receiver valve is normally open, parallel compression set point is set to flash tank pressure. So there's no reason for any pressure to make its way to the suction side of the parallel compressors to make them turn on. So we cause that pressure to rise by closing the receiver valve, which forces pressure to build, which will turn on your parallel compressors. And you get to set that how you want, when you want it to turn on within the software. So our next question is, how are the users controlling high pressure valve as a backup when the ejector block is utilized? I'm going to be honest with you, I haven't dug into that. It just came to light recently that most people put both valves. I've seen on this particular unit, it doing what I described earlier in cooler ambience, that it's kind of taken over with the high pressure valve. And then at a certain point, the honest answer is we've got settings that determine that. But if I tried to tell you what they were at this moment, I'd be giving you a hip shot, which I don't want to do. I'm going to respond to all of these questions, and I'll put a better answer in it for you. So we have another question. What risk of bleed by is there when both the high pressure valve and ejector block are piped into the system? I mean, bleed by, we're really kind of looking at, I guess that question would determine if you're using the high pressure valve, maybe you're kind of partially feeding one or the other. What really happens is you'll switch from one to the other. Like either you'll have if you had all the solenoid coils burn out on the ejector block, pressure's going to rise to a certain point and the high pressure valve is going to take over as a safety backup. So you're typically not going to have the high pressure valve doing its thing, with the gas cooler outlet temp and the COP line in conjunction with the ejectors. You're going to have one or the other, but you can set it up to where you get below a certain ambient, you move to the high pressure. You get above that, that setting that kicked on the high pressure valve, you'll move back to ejectors so you can start working on the Venturi effect and the lift for medium temp suction gas return. And then if you have both defined in the pack controller, it will by default use the high pressure valve as a safety backup should something happen to the ejector solenoids. Let's see, we have a question. Are the ejector nozzles able to modulate to adapt to load changes, or is it an on-off operation only? It's on-off operation only. I think it pressures that high with the small size of the components. It'd be really tricky to get a stepper type situation there, or to even pulse it. They're not even steps. Like the block we have here as an example has 6 cylinders for ejectors. It wouldn't be, let's pretend if there were 5 of them, it wouldn't be 20% across the board. It's set up more like 5%, 12%, 17%, so you can build different steps, but it is very limited compared to the 2,500 steps you would see on a stepper valve. Okay, so we're going to move on from the questions, but we will have a recording of the session available on YouTube on the Danfoss North America YouTube channel. That is the Danfoss North America YouTube channel. And we will also make a copy of the presentation available. And I think, do we have time for me to touch on the oil? Someone asked about oil earlier. Okay, so that was kind of the end of what I wanted to cover operationally. So someone asked earlier about, is the oil system different? So the first thing to note before we start going through slides, if we can get the unit view. So we have over here, and I don't think we need a close-up, Josh. We don't need it. We've got an oil separator over here, like a large Pringles can that we saw earlier. And then that dumps into this fairly large oil reservoir. One thing to note on the reservoir, you don't want to have 1,300 pounds in the oil separator being what feeds the compressors, 900 pounds pressure drop across your oil solenoids. So this oil reservoir is actually vented at flash tank pressure. So it's got a line that goes to the flash tank to stay at the same pressure. So in our example, this is at 520 pounds pressure at all times because there's a line going over to the flash tank. So if you think about that venting over there, there's actually a little bit of load coming from that dumps into that medium temp suction that we kind of don't show, but there is a little bit going over there as well. There's 3 control methods in our pack controller. The first one would be a system where this reservoir has just one switch, which is a high level switch. So all the control is going to be done based in and around the level of oil in your oil reservoir. So on a system with a single switch, it's going to be a high level switch. And basically that's going to tell you that switch trips, you know that the oil reservoir is full. So we're going to activate what we call an emptying sequence. So that trips, and then we start pulsing the oil solenoid with a solid state relay output. And on the pack controller, the two of the relays are solid state. And there's a sequence it runs through, which we'll look at in a little while, but it's going to pulse that valve on and off a given number of times in a given time period. And then once it runs through that emptying sequence, it'll stop. And then you'll just wait until the next time the high pressure switch is tripped. You'll run through the emptying sequence again, and you just do that in perpetuity. The second, which I think is kind of a belt and suspenders approach that I kind of like the best, is where you have both a maximum level and a minimum level, and you hit the maximum level, you start the emptying sequence, and you pulse the valve continuously over time until the bottom switch activates to let you know you've emptied the oil reservoir. On the first setup, you could theoretically be just emptying it a little. You're not really going to know it because you would just hit the one switch, run through the sequence, and hope that it emptied it. You have both switches, you'll guarantee that you've emptied the reservoir. And then the third option, which is more common than you'd realize, is there's no level switch. So that basically it's all done on timing, and it actually works pretty well. So what we would do in that scenario, let me let these pull up here. We would define that we have one separator, and then we would go in and physically jump a high level switch with like a wire jumper on an input that stays in there forever. And that initiates our emptying sequence at all times. And then you can define from there how often you want it to empty. So in this scenario, if you follow the little laser here, we're telling it when the high level switch activates, run through a full sequence. And that full sequence here, we've got 1 minute repeat time. And then basically the period time is 4 minutes, 240 seconds. And then a nominal time of opening. What all of that adds up to is when the high level switch is closed, that I want to open the pulse valve. I want to open the valve for 15 seconds every 4 minutes. And then I'm going to wait 1 minute. I'm going to do that again. And I'm just going to do that forever because remember, we physically wired in a jumper. So every 5 minutes, I'm going to open the dump solenoid for 15 seconds. And I just do that forever. That's a pretty effective means. And if you were dealing with that on a startup, having oil issues, either getting oil, if you were starving for oil, you might consider adjusting this nominal opening time. Increase that a little so that you're trying to get more oil out of the separator. So those are kind of our three options: high level switch only, high and low level switch, and then timing only. I hope that answers your question about the oil. And I think we've got more questions here, which is great because I'm out of material. So we have a question that says, what ratio was used to size the VFD for the medium temp compressor when compared to the torque current of the compressor? Is the compressor MOAs? All right, let me read that again. I think this question is going to be a little too complex to answer at the moment. I think I've got to reference some literature. Yeah, so I'll follow up and answer this one later. Kudos to whoever sent that. That was good. So we have a question. How would a CO2 system work in sub-zero ambient temperatures? I got that one yesterday. It's a really good question. If you think back to when we talked about the high pressure valve, you give it a minimum range and a maximum range. So regardless of what temperatures the gas cooler is seeing, if you tell it the minimum is 600 pounds, whatever temperature that equates to, let's say that's 50 degrees-ish. If you set that as the minimum, it's gonna close itself off to build the pressure in the gas cooler to not be above your minimum setting. So regardless of ambient, you're still going to have medium temp compressors discharging heat to the gas cooler. Let's say it's a block of ice up there. You're still going to be moving mass flow, able to build pressure because these are pumps. They move pressure. So your high pressure valve is going to limit the low end of a system, much like a drop leg regulator or your flood valve would do on an HFC system. Excuse me, how does the controller determine capacity required from ejectors? So it's basically defined. That's a great question. I had never had anyone ask that. So it's defined within the controller, not unlike condenser fan banks. You select a model for the injector. So I think the one on the table over here is an HP high pressure 1875. When you select that model, it knows what ejectors go in that, and it'll predefine the various capacities of the ejector blocks based on the model entered in the software. So in theory, you could have some control issues with an ejector block. Might want to check the model on the ejector block itself and verify that's what's defined in the pack controller. So we say, how many different CO2 racks setup are there? So there's actually a lot. So if you just take these three options, standard transcritical CO2, which typically would be booster and include low temp. So there's transcritical booster, then there's that same setup with parallel compression, and then again with ejectors that would also include parallel compression. But that's all on the transcritical side. You also have liquid overfeed CO2, pump CO2 systems. There's systems that use CO2 on the bottom side with HFC on the top side or ammonia on the top side. There's a myriad of different ways to do this. My personal opinion, what I've seen successful in the field for contractors to easily adapt to, and as well, much less expensive. Some of the liquid vapor separators on the liquid overfeed systems, they're extremely expensive. I think transcritical is probably what you'll see as the majority of the market moving forward. Efficiency greater than HFC systems. So have a question about efficiency of CO2 versus HFC, as well as initial cost, refrigerant costs, concerned about oxidation. So yeah, these are all, those are very fair questions. I had the pleasure of hosting a group of store operators yesterday, and they have a very different take on CO2 adoption than I myself would have about it. But as far as efficiency of the system, CO2 is a much better refrigerant. It just does more work. That's why you have smaller line sizes on the liquid. Doesn't take as much to do the same amount of work. However, there's a trade-off. The components, they're more robust. They cost more to build, so they cost more to buy. So there is absolutely an initial cost increase for a CO2 system versus an HFC. And then as far as the additional components to do the same amount of work, CO2 is eventually going to be regulated into your stores. Just to note, like in the countries in the European Union, just the European Union of Nations, there's 43,000 CO2 systems. A lot of those transcritical. In the U.S., we've got like less than 1,000. I think there's 900 and something. Canada has 600, so we're literally 1,500 for all of North America. So I know it's tough to spend the money on something, certainly if you're not buying the climate change or whatnot, but it is coming. The time to get familiar with it is here. The time to start specifying it is here. The last part of that question about the cost of the refrigerant, it's very cheap compared to HFCs. I want to say it's $100 a cylinder, something like that. So I hope that answers your question. And I don't know if we have any other questions. Okay, is there any plan to be able to program the pack controller through the 880 controller? That's a great question. And if I can get Josh for a close-up, I'll show you. So it's already included is the answer. One of these is turned on. Let me sign in real quickly. My apologies for not already being prepared. So this is the 880A that was referenced in the question. So the pack controller is already tied into this. Kind of the ecosystem for a store would be system manager, pack controller doing the system, and this governing the cases. The case controller's out in the store, but the high pressure control is already in the pack controller. So I can look here, see what it's doing. I can override the valve positions. I can do most of the things set point wise that I would need to do. This is our receiver control. So that functionality is already in the SM800. We've got our medium temp compressor shown here. There is also for the pack controller, if we come down one, there's also a remote display. We have a wonderful, easy to remember model number of MMIGRS2 for some reason. But this remote display, it will let you see the I/O for the pack controller. The system manager isn't meant for setup and configuration. It's meant for visibility and remote access to the pack controller. So you can't do anything with inputs and outputs here other than override some functions like compressors and fans and valve percentages. If you use our MMI remote display, it gives you full access to the pack controller, but it's a small display. It takes some getting used to. And then we have a software called Service Tool where you connect directly to the pack controller. So the interaction and the ability to make changes really is kind of good, better, best, with SM800A being good. This, as far as accessibility, better than the accessibility this will give you. And then the best would be our Service Tool software. I hope that answered the question. Do we have further questions? Oh, okay. So is there a class for how to operate the pack controller, specifically to how to navigate the controller and what data it displays means? So yes, I'm actually this week out doing training with pack controllers. We've got a pack controller training module you set on your desk, the desk in front of you. You plug your laptop into it. We load the software. We configure one. We go through the wiring, the issues at startup. We have a full day class specifically geared on CO2 and pack controllers. I think this particular unit is going to be here for a couple of weeks. It's going to the NASRC summit in St. Louis. Then I believe it's either out of the country or out of our hands from there. But if you would like individual pack controller training, please get in touch with whoever your local sales rep is. Let us know, and we'll put something together. We would love to spend that time with you. So we have a question. Can this pack controller be used with a lower model Danfoss controller? If the question is in and around, do you need an 880? Like we have the 880 that kind of does everything, HVAC, lighting, energy. Then we have the 850, which I believe just gives you HVAC and refrigeration. And then the lower level, the answer is it will tie in and communicate with any of the models. Our base model is the refrigeration controller, so all the functionality is built into that. And then really what you're getting for the higher models is building control functionality and lighting control. Did I say that right, Chris? All right. So our next question, it says in CO2, redundancy seems very important to keep a system running and not blowing off lots of CO2. What would you recommend for the best places to include redundancy for safety, service, and maintenance? The best thing is a generator. I mean, if I'm not the one writing the check, I want a generator that'll run most of the store, enough lighting so people can still shop the store. If you wanted a cost-effective way, I believe it's underutilized in my opinion, but I believe the single condensing unit that's just meant to handle load in a power outage situation, because you've got the heat exchanger that'll deal with whatever pressure's built. It'll keep pressure from building in the flash tank, as well as it's a very small load to have a generator for. So I think a backup condensing unit with a small generator and a heat exchanger to keep the temperature of the flash tank from reaching the relief valves would be the best option. So it says, what are some of the most common service issues with CO2 systems? I can't really speak to the service issues. That's not really my forte. However, I can speak to the startup side, and I see people struggle with the oil. Everybody knows if there's an oil problem, you need to dump in 2 more gallons, or that's the common misconception. It's pretty common. People put in more oil than they should because the pressure switch wasn't defined correctly. There's some other issue, and they wind up having to take that oil back out of the system. So see some issues, people getting the oil portion right. And then service-wise, I don't run service in that way. I kind of support startups and things like this. So I don't have a good answer, and I'd rather be honest. Any comments about the ammonia CO2 cascade system? Being that I of course have thoughts and opinions on it, but being that I'm representing Danfoss, I don't think I share it in this environment. I'm going to stick to mostly what we have on this particular unit. And since we don't have ammonia present, I'll leave it at that. When we'll see mass adoption of the Danfoss mechanical TXV for CO2, it's available. I have one in a box inside this walk-in cooler. We already have the mechanical TXV. I personally struggle to see where that would be used, other than maybe like a C-store application, box by box. And I'm assuming on that a small condensing unit with CO2 is still going to have some type of high pressure valve to give us liquid, but also to maintain just a limited amount of pressure on the TXV. But the mechanical TXV for CO2 exists today and is available. It is brought to you by Danfoss. Do you have any data on expected percentage of refrigerant loss per year on a CO2 system? I don't really have data on that. My guess would be the same people that put in the CO2 are the ones that put in the HFC. Whatever percentage leaks you see on the HFC, you probably see about the same on the CO2. Probably a fair guess. So we have a question asking about additional CO2 training at their actual training site. Chris, do you know if we have other training modules? We've got just food for thought. He's behind the scenes, but we have Chris Brown from Controller Talk Podcast. Chris Brown is here in the house. So I was through to him to ask if we have additional trainings. I do know that on our website, I can remember 15 years ago, you know, with CO2 were these large overfeed systems with liquid vapor separators. Most of the training that I did and the study I did was on Danfoss's website 15 years ago. If you go to our website and search for CO2 and learning, there are, I'm going to say, no less than 60 different presentations and modules to read through. So I would recommend our website. Yeah, yeah. Okay, so that concludes our presentation. I want to thank you all for your time. Before I let you go, if you don't mind, I'd like to thank Raul, who is our engineer handling the audio visual, Maria and Josh from our marketing team, Chris Brown, who graced us. He is unbelievable wealth of knowledge. He's a hero to everyone that works here. So again, thank you for your time. I hope you found it useful, and we will put in the YouTube channel recording a link to where you can get the presentation from. And just because I'm childish and it's our motto, I wanted to, before I say goodbye, let you know that at Danfoss, we're engineering tomorrow. Thank you.